Today, we are talking about post-training quantization methods or PTQ methods. We are going to refer to this concept as PTQ for the remainder of this video for simplicity. Now, PTQ is all about applying quantization techniques to make the model more resource efficient after it's been trained. There are multiple times in the life cycle of an LLM after it's been trained where you can apply PTQ. This means even during inference, we can keep optimizing it. So essentially, sky's the limit. We've looked at what's quantization and also pre-quantization in the previous episode. And this is why today's video is about post-training quantization methods. In a PTQ process, there are usually three things that happen. Weight quantization. The weights of the neural network, which are typically stored as 32-bit floating point numbers, are quantized to lower bit precision, such as 8-bit integers. This reduces the memory required to store the weights. Activation quantization. Similarly, the activations produced by the network during inference are quantized from higher precision to lower precision, further reducing memory usage and computational complexity. Determining the quantization range. An important step is determining the range of values that can be represented by the lower precision data type. This range is often determined through calibration techniques. So now let's talk about these calibration techniques. Static calibration. In static calibration, the range of activations and weights is determined offline using a representative dataset or by analyzing the statistics of activations and weights obtained during a pre-inference phase. This fixed range is used during inference. Dynamic calibration, on the other hand, adjusts the quantization ranges during inference based on the actual range of activations encountered for each layer. This approach can be more accurate but requires additional computational overhead. There's another subtopic we should talk about here, which is symmetric versus asymmetric quantization. In symmetric quantization, both positive and negative values are represented using the same number of bits, centered around 0. Asymmetric quantization allows for a wider range of positive or negative values by shifting the 0 point. Another subtopic we need to know is per channel versus per tensor quantization. Per channel quantization allows each channel of a weight tensor or activation tensor to have its own quantization parameters, which can improve accuracy. Per tensor quantization, on the other hand, uses a single set of parameters for the entire tensor. There are two important libraries that you need to know about: TensorFlow Model Optimization Toolkit and the NVIDIA TensorRT, which offer loads of quantization techniques and strategies out of the box, and all we need to know is which one is the most relevant for us. So let's learn about these. I'll show you 3 code examples now, and I'll also share a Google Colab file in the description tab of this video, where you can try these code examples out on your own. The 3 most common PTQ techniques are GPTQ. GPTQ is a post-training quantization or PTQ method for 4-bit quantization that focuses primarily on GPU inference and performance. The idea behind the method is that it will try to compress all weights to a 4-bit quantization by minimizing the mean squared error to that weight. During inference, it will dynamically dequantize its weights to float 16 for improved performance whilst keeping memory low. In our code example, we load the GPTQ version of the Zephyr 7B LLM. We create a tokenizer, initialize the model, and we create a pipeline. Then we structure our prompt, and after loading the model, we run our prompt. And as you can see, this is a technique that strikes a great balance between accuracy and performance. GGUF. Although GPTQ does compression well, it focuses on GPU and can be a disadvantage if you do not have the hardware to run it. GGUF, previously GGML, is a quantization method that allows users to use the CPU to run an LLM, but also offload some of its layers to the GPU for a speed up. Although using the CPU is generally slower than using a GPU for inference, it is an incredible format for those running models on CPU or Apple devices. Especially since we are seeing smaller and more capable models appearing, like Mistral 7B, the GGUF format might just be here to stay. In the code example that you see, we load the GGUF version of the Zephyr 7B, then we do the usual stuff, creating the tokenizer, pipeline, and the prompt, and we finally run it. As you can see, this generates way more relevant text than the previous technique. And even though 250 tokens have been specified for both, this one uses all these tokens in a much better way. AWQ. A new format on the block is AWQ, which is Activation Aware Weight Quantization, which is a quantization method similar to GPTQ. There are several differences between AWQ and GPTQ as methods, But the most important one is that AWQ assumes that not all weights are equally important for an LLM's performance. In other words, there is a small fraction of weights that will be skipped during quantization, which helps with the quantization loss. As a result, their paper mentions a significant speed up compared to GPTQ whilst keeping similar and sometimes even better performance. So in our core example, we get the AWQ version of the Zephyr 7B beta, use the AWQ quantization on it, set up the prompt and generate the output, and now take a look at the awesome output generated. It's just brilliant compared to the other two. So your quantization strategy is going to make or break your program. Do you want accuracy or do you want speed? You can't have both, not without spending a lot of money on GPUs anyways. By the way, if you've ever wanted pre-quantized models, there's this guy called the Bloke who shared pre-quantized versions of all popular models on Hugging Face. And you can get yours from there as well. Awesome. So we've learned post-training quantization today. And the best part, we didn't have to look at any maths. Now what I've realized from teaching more than 200,000 engineers across LinkedIn Learning, Pact, Udemy, and YouTube is that maths is scary for developers. So I'm trying to avoid it as much as possible because not all of us need to get into AI research. But I also know that maths is important to truly understand the concepts from a greater depth. So only after we've learned quite a bit, I'll show you guys the maths. Let's say after about 20 videos or so. I don't want you to get scared or intimidated just yet. Anyways, don't forget to check out other videos from my LLM concepts playlist and the AI plus LLM projects playlist. And also don't forget to like this video and subscribe. Also share this with your friends just because it's awesome free material.